0, 0, 0, 0 in it. There is nothing you can do to change that. Okay? Intel decided that when it comes out of reset, that is where the program counter will be pointing to.
God damn it.
So in your code memory, whatever's at location 0, 0, 0, 0 will be the first instruction that will be read, no matter what. And it's your job as the designer to make sure there is a meaningful instruction at memory location 0, 0, 0, 0 in the code memory.
Sorry, no. Could you sit there for a second? Let's just start recording.
I mentioned the EA pin. So this is this external access
because
pin.
I'm recording.
I'm supposed to be external addressing.
Thanks.
When it's low, basically we effectively switch off the internal code memory. When it's high, we use the internal code memory. But if we go beyond the limit of the internal code memory, it may well go to external code memory and try and find it there. Generally speaking, when you're building a system, if you want to use as few external devices as possible, you try and buy a device that has all the code memory you need inside the device. And then you would normally have the EA pin wired high to tell it, no, I want you to be using the internal stuff, and hopefully that will be sufficient. Because you've seen as soon as we start to use external data memory, external code memory, we start to lose a lot of our pins on the device. And as a controller, we want to have lots of pins to control heaters, lights, do all those fun things. So preferably, you would buy a device that has sufficient data memory and code memory internally. Okay, so done that pin. The ALE pin, you don't directly control it yourself. It's used by the microcontroller when it's accessing external memory. Automatically, it will be controlled at the right time by the system. So that could be used, it's used for both when we're accessing external code memory or accessing external data memory.
Can it be used from behind?
And it's specifically used to control a latch. And in fact, taken from a book, here's an example of someone that's wired up an 8051. In fact, this is an 8031, it's got no internal code memory. And it's showing you a way of wiring it up to external program memory, external code memory. There should be no surprises here. So here's port 0, and you can see the wires from port 0, they go to the input side of the latch, but they're also going around to the data port on the code memory. So they're going to two places. The ALE signal is going to the gate control for the latch. Now they've drawn one of these, there's 8 of those little flip-flops built into that latch. Port 2 is going directly to the upper part of the address, and the output of the latch is going to the lower part of the address, just as I've shown you. And then we can see what's happening with some of the signals up here. Now, in fact, we're not using the read and the write signal because whoever's building this system, they're talking about accessing external code memory. And the read signal for external code memory is this P-send signal. So you can see that as being wired up to these pins. CE stands for chip enable, OE stands for output enable. Output enable is another way, a fancy way of saying read. So what happens is when P-send goes low, this chip becomes enabled and the read access happens at the same time. So that's an example of wiring up an 8051 type system to external code memory, similar to as I've shown you. Yeah?
74 less
It does, and they've not shown it, but there would be a ground pin. They're being a bit naughty.
What the fuck?
Okay.
You just try to kiss the stereo thing.
In fact, this is now showing you the timing that goes on associated with that previous slide. And there was an exam question one year where this was actually put in the exam paper, and the students were asked to explain step by step what's going on in order to complete an access from the ROM. But I won't be expecting you this year to go through this in that detail, so you can probably breathe a little bit of a sigh of relief. So this is showing you the fetch cycle for fetching an instruction from external code memory. And you can see what's happening to port 0, port 2, the PSEN, the ALE, and the oscillator. This is actually not the complete cycle. This is showing you fetching the instruction itself. But if the instruction had some data associated with it, like an operand, that would have to happen afterwards. This is just what has to be done in order to fetch the instruction. So if we go through it step by step, you can see the first thing that's happening here is, when you see this, by the way, there's no writing in it, it means that we're not interested in what's happening at this point in time. Here, it says PCL. That stands for Program Counter Low. So at that point in time, the microcontroller will put onto port 0 the contents of the program counter. But the program counter is 16 bits wide, remember? So the low 8 bits of the program counter gets stuck out onto port 0. At that same point in time, the ALE signal goes from high to low, and that's the trigger for the latch to lock in the information. It's not a low to high transition, it's a high to low transition. So at that point in time, the low value, the low byte of the program counter will be locked into the latch. You can also see around about this time, port 2 is writing out a high byte of the program counter. So that's PCH, program counter high. So from that point onwards, port 0, well, the latch is holding the program counter low, which is not shown on this drawing, the output of the latch, and the high part of the program counter is held on port 2. So the complete address is now available. Now, because we've latched the low part of the program counter from port 0 into the latch, at this point here, we don't need port 0 to do that anymore, because the latch is holding that information. So we can now use port 0 for something else. And you can see a little bit further on, blah, 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 down here, PSEN goes from low to high. Now, in this particular case, it's the low to high transition that causes whatever's on the data bus to be brought back into the microcontroller. So, at that point in time, we've got the high byte of the program counter on port 2, the low byte of the program counter held in the latch, because that's the complete address. We have a low to high transition on PSEN, and at that point in time, that effectively, the data that's in the program memory will be out on the data bus, and that will be sampled by port 0 and fetched into the instruction register, which is what's happened there. That's taken us, by the time it's done this, there's a few more bits and pieces here, but generally speaking, to complete that whole cycle, the oscillators had to go up and down 12 times. So it's taken 12 clock cycles to effectively bring the instruction in from the outside world and execute it. During this last phase here, this is where the instruction will be interpreted and some action will be taken.
Is there no way of showing the diagram what way it's going? Or you've got to know?
Yes.
Well, you won't get a diagram like this in the exam, so you don't need to.
Is that opcode is going into the controller?
I've not come across a timing diagram that shows that. There may be a way of doing it, but it's not normal to show.
Just
Because
annoying
that
when you
opcode
watch
goes
it.
in, right?
That opcode is
That's
going
so
from
bad.
the RAM, from the ROM into the microcontroller.
Especially when you turn the
Whereas that's
speakers really
going out
loud.
back like that. This is change of direction.
That's good.
I wonder if S1
That's, yeah, that was
Right, I'm going to talk through that. Basically, in order to, these are the different phases of one machine cycle. So this is step 1, step 2, step 3, step 4, step 5, step 6. Effectively, in order to do all the things it needs to do to fetch this instruction, the microcontroller is actually having to do a sequence of actions. And that sequence of actions is shown here as these steps. In order to complete the action of actually going to external code memory, fetching a byte, putting it into the instruction register, and interpreting it, it would take us 12 clock cycles or 6 steps to achieve that. So if you have a 12 megahertz crystal, that means it looks like you're doing 12 million things a second. But actually, the operation of fetching an instruction, it will take you 12 clock cycles to achieve that. So in order to fetch an instruction, it will take you 1/1,000,000th of a second, not 12 times less than that.
For example, if I'm using 8 megahertz crystal, can I still achieve the same?
You can't, if you change the crystal speed, you will change the speed that everything happens here. So, and this is a crucial point, if you choose to have a 1 megahertz crystal, basically everything slows down. Everything takes longer. So if you want your microprocessor to, I don't know, control some video display, and it has to achieve its task within a certain time, that might put a limit on what clock frequency you need to use. So you need to pick the right kind of frequency, one that's fast enough for your job. Now, the manufacturer will give you an upper limit. They'll say, you can have any crystal you like up to this speed, but beyond that, the thing won't work properly. Going down, most members of the 8051 family, there is no lower limit. So if you wanted a 1 hertz crystal, not that you could get one, if you did, you could have one. And this thing would go incredibly slowly, doing whatever it's doing. In fact, most members of the 8051 family, if you stop the oscillator, it will freeze and hold on to exactly what it's got. And then when you start the oscillator again, it will carry on. So we often say it goes down to 0 hertz.
For example, if we execute a program of blinking the LED,
Yeah.
so
Depending on the crystal, the LED will blink at different speeds. Yes.
Stop that.
So you can see it takes 12 clock cycles to complete what we call one machine cycle. Now, in this case, if the instruction was something like int A, where there was no operand, then when we fetched it in phase, in if you like, step 4, in step 5 and 6, we could execute that, doing something with the incubulator, and everything will be finished by the end of step 6. So some instructions, to completely execute that instruction, will take one machine cycle. Other instructions, you have to, for example, if we did move x a 1, 2, 3, 4, that's going to take more than one machine cycle to do its job. It will take you one complete machine cycle to bring in the instruction, which is actually move x into the accumulator from a direct address. The next step will actually then be to start fetch this information out. So it may take 2, it may take 3 machine cycles to complete its task. If you look at the Intel datasheet for the 8051, for all the instructions it supports, it will tell you how many machine cycles each instruction takes. So most of them take 1, some take 2, I think some take 3, I don't know if any take 4.
Is step a universal thing as 2 pulses?
There may be other microprocessors that use less steps. And in fact, there are versions of the 8051 where effectively it can achieve everything in one step now. But in the classic 8051, it took 6 steps, 12 oscillator cycles. But no, there is nothing that's generic about that. That's this particular device. Now there may be others which do the same thing, but there could be others that might have 4 steps or 2 steps, and how many oscillator cycles per step. I think probably 1 step is considered one. Well, I don't know if it's 2. I don't know. No, I couldn't answer that. Don't know.
Fair enough.
and why do we use capacitors in the oscillator?
I swear, it's really Jumper Friday, isn't it?
I don't know why, is the short answer. It's a resonance circuit, and I think probably the crystal acts as like an L and the capacitors at C, and you need something that's kind of a flow of charge backwards and forwards at a resonant frequency. But you need that charge to be stored somewhere temporarily before it flows back onto the resonator. So I think that's why, but we're getting down into really low level stuff that's not in this course for sure. Okay, let's move on. Right, now I'm going to talk about port 3. And you are expected in the exam to be able to know about all the ports, what port 0, port 2, port 1, port 3 do. And in the case of port 3, what the alternate functions are for port 3. Now, I wouldn't, in an exam, expect you to know which particular pin has which particular function. But I would expect you to know,
Cut his legs off.
across port 3, what are all the functions which are supported. So here's a list of them, and I'm going to briefly go through them. Okay, so the top two, port 30, port 31, those two pins say RxD, TXD. They are associated with, inside the 851, there is a serial interface. So there are special registers built into the 851.
Okay, so you're getting annoying now.
There's a pair of them which are actually known together collectively as SBUF.
Just pay attention.
Stands for serial interface buffer. And there's another register called SCOM, which stands for serial control. SBUF, the input and the output, are hardwired to those pins. So this one is connected, this is the TXD pin, which is port 31. And this is the RxD pin, which is port 30. You cannot change that. Intel have internally wired that pin to the buffer and this pin to the buffer. You might say, well, why do I care? Why do you care? Because, might not, I don't know. One of the clever things that can happen is if you have some data to send, if you write it to SBUF, the microcontroller will look at user timer and it will determine precisely how fast to send out that block of data without you having to worry about it. So if you've got 8 bits of information to send out, like a character, you know, basically you just write your 8 bits into this buffer and then you can go and do something else. You can make a cup of coffee, go watch some telly, do whatever you like. This will automatically be sending out those 8 bits at exactly the right speed. The same way that if anything happens coming into here, this will automatically capture it and store it in this buffer for you and set a flag saying, hey, something's arrived. Now, you don't have to use it, but if you're going to use the serial interface, you'd be probably foolish not to use it because it makes the programmer's job so much easier that these low-level functions are done for you. So that's the first 2 pins. So the transmit and the receive pins for the serial interface. The next 2 pins, 3.2 and 3.3, it says int 0 and int 1. They are external interrupt pins. The microcontroller will be busily working its way through a program and doing whatever you want it to do, but sometimes you actually want it to be able to stop doing what it's doing and to pay particular attention to something urgent that's just happened. Each of these pins can be wired up to something externally, such that when that happens, it stops doing what it's doing and will go to a very special part of the code memory and try running the program from there. An example might be you connect your brake pedal of your car to one of these pins, so that when you hit the brake pedal, you don't want it doing some whizzy display. What you want is to stop the car. So that's much more important. So external interrupts allow you to be able to do things like that. Is to take control of the microcontroller, stop it doing what it's doing, and tell it to go and do something special. And you have 2 pins for doing this. Yeah?
Are they, can they count as 4 interrupts?
Each one of these has its own special interrupt. It goes to a special place for each one of those. You can wire up multiple sources of an interrupt to it. So you might have 4 things that are all wired up to that one pin. But then the question is, well, which of the 4 caused the interrupt? You would then have to write some software to go and interrogate to find out which one caused the interrupt.
I mean, if you write like 0, 1, and then like 1, 1, or 0, 0, can they represent it?
No, it doesn't work that way. No. Effectively, you can either have what's called level triggered or edge triggered. But if they were level triggered, when one of them goes, for example, low, the interrupt happens. If the other one happens and goes low at the same time, you'll effectively cause 2 interrupts. One of them will have priority over the other one. It will do its job, and then the other one will be dealt with. But no, you can't like demultiplex it into more. No, that's not possible. The next 2 things are connected to timer 0 and timer 1. The 8051 has 2 timers built into it. Now, you could use this, for example, to, rather than use the microcontroller's internal clock to increment the timer, you want to use some external clock source. That's one reason. Or you can actually use these timers not as timers, but as counters. for doing things like counting widgets. So it might be that you've got a conveyor belt, and when 24 widgets have gone past, you want the microcontroller to do something. Well, this pin could be connected to some kind of flap, and every time it goes up, it counts one more. So it's not linked to any specific time, you're actually using the timer as a counter. So that's what these two pins could be used for. Either as an external source of timing, or to act as a counter. The next two pins, in fact the last two pins you have to worry about, are pins 3.6 and 3.7. And this is if we're using external data memory. If we're using external data memory, then the microcontroller will assume that pin 3.6 is your write signal to the external data memory, and it will assume that pin 3.7 is your read signal for external data memory. How will you be using external data memory? There is only one way ever to access external data memory. If you never use that instruction, you're never using external data memory, so you don't have to worry about those pins. But if you are using external data memory, then you have lost those two pins, whether you like it or not. They will be used by the microcontroller, the read and the write signal. And there's nothing you can do about that. Okay, so here's, we had one diagram showing how to wire up the 8051 to external code memory. Here's an example of wiring it up to external data memory. Now you could do both, but in this case we're assuming that we're using internal code here, in which case we're not doing anything with pSend. You notice that signal's not going anywhere. We're not trying to access external code memory. But we're probably in our code somewhere going to be using these MoveX instructions. And because we're using the MoveX instructions, we've wired up all this external data memory here that could be holding temporary information. We've been logging the temperature of something, or I don't know. You wire it up in exactly the same way as you would for the other case. So port 0 needs this latch again for the demultiplexing. Port 2 provides the high part of the address. In this particular case, part of port 2 is using something called address decoding logic. And later in the course, I will spend almost a whole week talking to you about address decoding, which you'll probably find incredibly boring, but we'll get through it anyway. So I won't go into any details on this at present, but effectively, this device will only wake up when there's a particular combination of ones and zeros on the address bus. And then you can see port 3, 6, and 7 are being used for the read and the write signal. Right, it's 10:30. I could start the next topic, but how many of you have got a stomach for another 20 minutes, and how many of you would rather we just call it a day and we do a 7-language programming part 2 next week? Who wants to do it next week? Who wants to carry on? Oh well, that's a bit. All right, so next week, for all 3 hours, we'll be doing a 7-language programming, and there's quite a bit. There's only 30 slides. There's a lot of material to get through on that 30 slides, so it's going to be a busy week. Probably the hardest part of the course. So
Fair enough.